Our speaker is Professor Jerzy Kowalski-Glikman, and the title of his talk is "Why There is Almost Nothing Rather Than Something," and subtitle is "The Cosmological Constant Problem." Please, Jerzy, begin.
Okay, thank you. Okay, let me start. I would like to tell you about the cosmological constant problem and the possible way, well, not the resolution, but the way to resolve it. And let me see. It's too much. Okay, good. So the plan of the talk is, which one is a pointer? You should use a stick. Yeah, okay, good. Everything good. So, so the plan is, there are two parts to it. What is the cosmological constant problem? So I'll try to describe why there is a problem, why people consider it as a problem. And then I would like to argue that one of the aspects of the problem, which was not that emphasized or just simply missed, is that this problem is actually have two sides. It's ultraviolet and infrared side of the vacuum energy. And then after realizing that, I will actually rewrite the relevant expression that I will try to explain. Well, here, I would like to express it in terms of the regularized phase space expression. And then I will invoke holography to find a bound on a cosmological constant, which actually agrees with observation. And this is based on a couple of papers. One is this research paper that appeared in December, and another one appeared less than a couple of weeks ago. It's an essay written for this gravity essay competition. So these are these two basic sources on which I based the talk. So, well, before let me actually start with explanation of the title. The question why there is something was asked first. Well, it was not asked first, but it was made a kind of an important question and was phrased forcefully by Leibniz early in 18th century. And this is considered to be one of the basic questions of metaphysics, why there is something. And then this was a title that's why I pick it up, because it was a title of pretty famous paper of Sidney Coleman of late 80s, in which he actually tried to address the very cosmological constant problem, asking why there is nothing rather than something, so why the cosmological constant is zero instead of being some number. The thing actually changed since then, because now we know that there is something like that, there is a dark energy in the universe, and the easiest, the simplest explanation for dark energy is a cosmological constant. So now the question is not why the cosmological constant is actually exactly zero. The question is why the cosmological constant is small, relatively small, and let me explain what small means. So unfortunately, because now we have PDF, this nice, beautiful GIF that this spring was actually moving up and down is now still. And that was the reason that why I wanted to use my original file, but doesn't matter. Imagine that this guy is actually moving up and down. And in quantum mechanics, we know that there is a ground state of vacuum energy. Every oscillator has a ground state energy, which is essentially equal to, it's related to the frequency of the oscillator. Then in field theory, the situation is a little bit more, well, in a finite dimensional oscillator, you don't really care. And in field theory, actually, as I will explain, you don't care either, at least in most of the applications. But in field theory, the problem is more severe because the field theory describes an infinite number of oscillators, essentially one oscillator per value of linear momentum. And then, since it's an infinite number of them, if you adapt the energies of this vacuum fluctuations, you get this expression. And when you do the integration, it essentially, well, this expression is, of course, divergent, but then you can write it essentially in this way as a limit of some energy scale going to infinity of the force power of this energy scale. This is of course infinite. And what people do, of course, they put some cutoff here. So they replace this limit with a kind of a finite, value of this parameter lambda. Now, the very fact that the vacuum energy is infinite or cut off by some scale is not a problem in, well, the standard flat space quantum field theory, because if gravity is not there, then the only thing that matters is our energy difference between the states. And this infinite addition of energy to any state simply drops out, cancels out from the calculation. And there is this standard procedure of using normal ordering to get rid of this infinite contribution to energy. However, if gravity is present, the situation changes, or at least we believe it changes, because gravity is universal and every form of energy and momentum actually is a source of gravity. So if you have an infinite amount of energy, infinite amount of vacuum energy, it produces an infinite gravitational field. Well, you must be a little bit careful about that because this is a statement that in a sense goes beyond any experimental facts that we know. We never measured actually the vacuum energy contribution to gravitational field. There are some, so the question if the vacuum fluctuation actually produce gravity is the question. So the natural question is that they do, because otherwise we would have a lot of problems. I mean, the reason why some form of energy is not to produce gravitational field, it would, if it doesn't, it would really give us more headache than if it does. But strictly speaking, there are no experimental tests, and there are some experimental tests going to be performed next year. This is using the Casimir effect and the weight associated with the vacuum fluctuations in the Casimir cavity. But let me assume, for the sake of the argument, let me assume, as everybody does, that gravity is universal, which means that gravity actually is the source of gravity is also vacuum energy. All right, so okay. Then, so what is the cosmological problem then? Well, the problem is the following. The gravity action naturally contains a cosmological constant term. And well, you may argue incorrectly that, well, the vacuum energy, so the cosmological constant term is just a number, it's just a coupling constant in the action, which means that you may say you can account for, well, I don't know, dark energy, but just by adjusting the value of this parameter to the observations. The problem is that this completely misses the point. The point is not what is the value of the parameter in the action. The problem is actually that if we believe that vacuum fluctuations are source of gravity, then the vacuum fluctuation of any field theory actually contribute to this. So effectively, the energy momentum tensor, in the sense that I'm going to explain in a moment, just gives a contribution to this term, which is uncontrollable, which can be, well, in principle is infinity, but then you can regularize it, and natural regularization are part of the experimental bound. So the problem is not about this parameter in the action. The problem is that there are loop contributions which have exactly the same form, which actually are infinite. So how it actually works? Well, you can, okay, so let me look at the simplest source of this kind of term, which is basically the linearized gravity. So let me assume that I am in a semi-classical setup. I have a linearized gravity, so the action, so the contribution of the action of energy momentum tensor is essentially this one. And then I can compute the vacuum to vacuum amplitude, so the vacuum to vacuum expectation, or the vacuum expectation value of energy momentum tensor, and then it's going to contribute, if it's non-zero, it's going to contribute to the term which will look exactly like a cosmological term. So this is the kind of this loop contribution to the action. And then in the leading order, the relevant diagram is a kind of a loop diagram coupled to one graviton line. And this diagram actually looks, so if you actually compute this diagram, it actually has this form. And then you do the calculation, and as a result, you get something which is essentially proportional to the force power of the cutoff. So what is relevant about this calculation? It's essentially telling you, first of all, it tells you that there is this cutoff needed here just to make this contribution finite. And this is the relevant reference for this calculation, in which this calculation is actually discussed in details. Yes? Okay. And what actually is telling you is that this calculation is essentially telling you that if I have that the effective contribution to cosmological constant is essentially the vacuum, the value of the vacuum, kind of a vacuum of the circle vacuum diagrams, actually put as an energy density to the action. So the loop contribution is essentially contribution in the leading order, again, is essentially contribution of the loop diagrams. Now,
explain again what is this propagator which is written here?
So it's a skeletal propagator, but there is an energy momentum tensor, vacuum to vacuum amplitude, so that the derivatives and the derivatives produce this T values.
So it is supposed to be vacuum energy, huh?
This is the vacuum energy. This guy is essentially this vacuum expectation value of this operator for the skeleton. Right, because the vacuum, the energy momentum operator contains derivatives, right? Contains particularly contracted derivatives of momenta. So and then if you do the vacuum energy, if you compute the expectation value in the vacuum, you just get this thing.
This matter is of scalar field. Yes.
Yeah, this is
scalar.
Sorry?
Matter is scalar.
Yes.
Scalar.
Yeah, just a scalar. But of course, you can do exactly the same thing for higher speeds. Right. Okay, can I continue, or are there any questions? Good. So this rough calculation, and I say again, I said that this is rough calculation, and the details can be, for example, read off from this paper I mentioned. it tells you essentially that in order to compute the cosmological, the loop contribution to cosmological constant, the vacuum energy contribution to cosmological constant, we must compute the loop diagram and multiply it by square root of minus g and add the result to the action. So this is essentially the contribution. Again, in the leading order. All right. So now, what is the problem? What is the cosmological problem? The problem is that if you actually do that, we are in trouble, because the measured value of cosmological constant, we know it's not 0, but it's enormously small. It's 10 to minus 120 essentially in Planck units. And then, depending on what is your favorite cutoff scale, right? I mean, you can cut off. You can make this lambda into the favorite cutoff scale. The natural one will be, of course, the Planck scale, because we believe that it has something to do with quantum gravity. And then the lambda is going to be 1 as compared to 10 to minus 20. If you want to have this 10 to minus 17 as a standard model scale, then we have the discrepancy, which is not that large, but it's still many orders of magnitude and so on. So which, of course, you can also argue that you may associate this cutoff scale with the supersymmetry breaking scale, because the supersymmetry, in supersymmetry the cosmological constant is 0. But still there's gonna be still there is this discrepancy. Clearly, the problem is that the cutoff that we're using normally you would use is the ultraviolet cutoff, and then this vacuum energy is highly in infrared. So there is a huge discrepancy of scales. And it's also related to the enormous hierarchy of scales, right? Between the scale of between this infrared scale of vacuum energy as measured in the by the cosmological constant, and the ultraviolet scales. Well, there is I have a small comment about the string theory. The string theory is finite, ultraviolet finite, but it doesn't need it, so it doesn't need the cutoff. But then there is a problem, because if you think about string, the string, not superstring, there is the computation of the vacuum diagram is still, it's finite. Well, it's ultraviolet finite, but there is this infrared problem associated with the tachyon. And even if you remove the tachyon somehow, you just cut it off, then still the expression is proportional to the string scale, which is again close to the Planck scale, which means that we're still having a problem of discrepancy of scales. So string theory, even though it's ultraviolet finite, at least for this calculation, it still doesn't solve the vacuum energy problem because of the tachyon. And if you use a superstring, it doesn't work either, because the superstring require negative or 0 cosmological constant. Okay, so what is the idea? So now let me actually start doing the calculation. And the calculation I'm doing, I'm going to present actually just reshuffling of this basic integral that we need to do. So the basic idea is to consider this kind of integral, which is essentially the integral over loop. So instead of considering the vacuum Feynman integral, I can consider a particle. I can consider a particle integral over the loop. The idea is that the field theoretical integral is essentially a sum of integrals over possible particle momenta, right? Or possible particle masses, or possible particles that actually move on the circle. So that it can be actually reproduced by just the particle integral. This is just a particle integral around the loop. Tau is the parameter that actually is the just a parameter labeling the points on the loop. and you have this 2 tau factor in the measure because you want to get rid of gauge invariance associated to the fact that there is this translation invariant along the loop, and there is an orientation invariant along the loop. So this is the orientation invariant is the source of this 2 factor, and tau actually removes this. It's essentially the Faddeev-Popov determinant, which is associated with gauge fixing of the translational symmetry along the loop. And it can be showed, I don't know how, okay, well, it can be shown that this is exactly what we're going to do, what you're going to get if you just do the vacuum path integral. So the partition function for the vacuum partition function for the scalar field is this thing, which can be expressed in terms of the determinant, which again can be expressed in terms of exponents of trace of the logarithm. And this boils down essentially to the same integral that we have before. This is essentially the loop integral. So we see that the vacuum partition function is exponent of the circle partition function, where the circle partition function is actually computed to be this thing. Well, I will because this volume factor here is going to be essential. So let me talk about it in a moment. But then if you compute this circle amplitude, it actually gives you this vacuum energy times the volume of space-time. So the circle amplitude is essentially given by vacuum energy, which is the standard expression, times the space-time volume. Okay, so let me actually.
But it seems that this first integral seems to be very finite.
Which one?
This exponential function feels this. And the second integral is obviously ultraviolet divergent.
No, why you think?
Because there is the exponential function which suppresses this ultraviolet domain.
But there is this tau integration that actually brings it. Well, if you do the technical calculation, actually compute this tau integration first, then you find the expression. This is essentially this one. So if you integrate over tau and then you integrate over k0 in the standard way, then what you get is this expression.
This is
kind of a Stinger. This is kind of a I'm not an expert in this, but this is kind of a Stinger. The tau integration essentially brings you the propagator, and then there's integration over k gives you this equation. We can do it.
Okay, but order of integration obviously matters here.
Order of integration always it always matters. Well, you need to regularize. I mean, these expressions are obviously infinite, so you need to regularize somehow. But well, I'm not completely sure. Well, the tau integration is actually. Well, okay. Well, could we discuss it?
But what is omega p?
Omega p is p squared plus n squared squared. Just energy.
But p is k.
Yes, p is k. Yes, that's yeah. P is of course, p is k. Good. So let me actually get back to the expression for the circle amplitude, and I wrote that the circle amplitude is actually a trace of, well, now I'm still in I'm because the computation before on the previous slide was actually done already after Wick rotation was taken. So now we are back in Lorentzian space-time, and the trace that is used there is essentially is defined to be as a trace in momentum space of the Hamiltonian constraint operator. So in the case of a particle, it is just p squared plus m squared. Now, so the trace is actually this kind of expectation value. But notice that this kind of expectation value, since the Hamiltonian operator is diagonal in momentum space, just produces for you delta 4 of 0. Okay, and this is just the eigenvalue of the energy. And now delta 4 of 0 in momentum space, delta 4 of p in momentum space is defined to be this thing, right? It's just the Fourier transform of this object. But if then the delta 4 of 0 is exactly the same thing, but with momentum being equal to 0, which is nothing but the volume of the space-time.
Could you explain why the delta 0 should up?
Well, because you have p mu, right? And this guy is diagonal, so this is p mu, which is delta of p minus p.
Okay, but you move out the eigenvalue, and then the state can be normalized, and then there should be unity instead of, why not?
Well, the plane waves are not normalized. Well, you can, of course, you can always use the localized, the wave packets. Okay. But we just want to have just a plane wave basis. So one way or another, if I use the wave packet actually to be in some finite volume, then of course I can do that. But one way or another, I obtain the volume factor. So my point is that since this thing is just a volume, I can rewrite this expression as instead of rewriting it times a volume and times momentum integral, I'm writing this expression just by the phase as a phase space integral, which is the crucial step in the reasoning. But I want to stress that nothing really happened here, right? I just rewrote the same expression in a different form. Okay, so first of all, let me leave out the tau integration and concentrate on this phase space integral, which is again just a trace in momentum space of this expression. And now I will try to rewrite it again. Again, nothing really happening here. Let me rewrite this integral in terms of the following. So this integral here can be written as product of this of the four integrals. And then let me actually, instead of writing the integral over the q and the p, let me actually write p and q in terms of some momentum scale times a variable that goes from 0 to 1 and some momentum scale lambda for position with another variable going from x from 0 to 1, and then this expression can be rewritten as the integration of these variables over cells x and x twiddle of finite size from 0 to 1, and now we need to only sum up over the cells, right? So instead of having the whole phase space, I decompose the phase space into cells. There is it's going to be, sorry. There is a figure here. So instead of integrating over the whole of the phase space, I actually decompose the phase space into cells, and then I sum over all of the cells. So again, nothing really happened here. Is just the expression the integral in terms of the integral of the whole space into the sum over integrals over finite cells. Nothing. The thing which is important here is that, in a sense, I would assume that these cells are actually kind of a minimal in sense of quantum mechanics. So I assume, oh, this is not nice. I assume the constraint between which is satisfied by the momentum scale and the length scale, which is just the fundamental, which just essentially is the fundamental quantum constraint. That means that the quantum mechanics essentially is telling you that the cell in phase space, there is a minimum area of the cell in the phase space, which is given by uncertainty principle, which is this one. So the product of the moment energy scale and momentum scale is actually given by position
and momentum.
Position and momentum, yes. There's position scale, lambda, and momentum scale, epsilon, and I assume that they are minimal. So in a sense, what I'm assuming now is that I'm not actually decomposing my space into arbitrary cells, but I'm decomposing my space into minimal cells. Okay?
Classically, both epsilon and lambda go to
what I'm saying is, well, this is quantum mechanical calculations, right?
yeah, but started with integral along classical phase. So that integral they should be both in. Yeah.
No. Well, okay. Well, the integral for integral it doesn't matter. So what I'm only saying is that I'm decomposing my phase space into minimal cells quantum mechanically. That's it.
I think those cells are by definition.
The cells are by definition minimal, and this is okay. But of course, nothing forces me to identify this epsilon with Planck mass and this lambda with Planck length. There can be anything in this calculation. The only thing that I'm considering is that, I mean, quantum mechanics tells me that I cannot really go beyond better than that. Okay? So the sums can be interpreted as counting. Well, the things are called in the theory of something which is called modular quantization, which is explained here. This is a fundamental object to start with. So instead, this is kind of a unitary equivalent representation of quantum mechanics, in which instead of having position representation or momentum representation, actually you have a representation in a kind of a finite cell. Okay. But this is a textbook.
Everything is under control.
No. You mean this one?
Okay.
No, this is the book by Haronov, with I think mostly by Haronov, because this is essentially said. So the book is about resolving quantum paradoxes, not about stating that there are paradoxes, but about resolving them. All right. So this is something that I showed you about. One thing that I would like to stress here, that instead of having in this procedure, instead of having minimal length, area, and volume, and so on, we have a minimal size of phase space. Okay, good.
Technically, it means that your initial integral of the space and momentum are not independent from each other, but there is this constraint, this size of it.
No. Well, this integral, I'm not sure why you. Well, let me. I guess I have this integral here. This is what the integral is, and
The size of the cells in momentum and
well, the size of the cells. Well, I still integrated over whole. I mean, the integral that I have here, which is this one, right? It's still the same integral as it was before. For a moment, I actually choose the scales to be completely arbitrary, except that they are minimal. And the integral is exactly the same integral as it was before. This is just a writing of the same integral. So nothing really changes. I mean, the form of the integral changes, but still is completely general. What happens to be a crucial step, so I think I forgot this numerical factor here, is that now I can actually, the integral that I had before, so this one here, is still the summations over all integers. So the integral is clearly divergent. But notice that it is divergent not only in ultraviolet. The ultraviolet means very high momentum, but it's of course divergent also in infrared, where infrared is actually the very large space-time volume. So I need to regularize it. Well, there is nothing wrong about regularization, but nothing particular. I mean, we always regularize the infinite integrals of quantum field theory. So this is my regularization. I actually assume that the number of cells in momentum space is NP, and the number of elementary cells in space-time is Q and Q. There are these two numbers. I don't know what they are, which means that the size of the size of space-time is L, which is NQ times the scale lambda, and the scale and the size in momentum space is M, which is NP over epsilon. So I have both momentum space and space-time regularized. Okay. The total number of cells is actually given by these two numbers. Okay, this is the force power of the product of these two numbers. This is the total number of cells. So what we're having at this point, after making this integral after regularizing this integral, we're actually getting the integral of a finite phase space, where the dimension on the number of cells in the phase space, or the volume of the phase space in Planckian unit is just n. Which can be also written in this way. So number of n is essentially the size of the size of the space-time times the size of momentum space divided by this 2 pi h bar to the power 4. This is the volume of phase space in Planckian units. So this means that if I regard this n as fixed, then L and M are essentially cut off. The L is infrared cutoff, which is the cutoff on the size of the space-time. M is ultraviolet, kind of momentum cutoff, which is the size of momentum space, but they are not separate, they are not independent, but they are related by this kind of seesaw formula. And I would also should mention that the seesaw formula actually appeared already in a similar, but not complete, but kind of a different but related context in the famous paper by Cohen, Kaplan, and Nelson, something like 20 years ago, in which they actually wanted, they noticed that in order to make sense of entropy argument, you really need to have this kind of a seesaw formula, and then actually start checking if in the context of effective field theory, this kind of seesaw formula actually makes sense. So it doesn't have any observable consequences in high energy physics. And it turned out, so they actually found what are the constraints on L and M so as to avoid the consequences, measurable consequences in particle physics. Effective field theory. Okay, so if I have this partition function, which with regularized partition function, I actually can compute the vacuum energy, because you remember that the partition function, this circle partition function, was the product of energy density times the space-time volume. So I can actually compute using this partition function. I can compute the vacuum energy density, and then assuming, well, we still have this tau integration to do, but and we don't have a solid theorem, but from what we've been able to check, this tau integration doesn't change substantially this value of the integral. And when you actually start investigate this integral, you find that there is this vacuum energy density satisfies this kind of inequality. So the vacuum energy density is actually bounded by the epsilon times NP. So epsilon is our scale, and P is a number of momentum direction cells, which can be written also in this case. So if I identify M with where M is essentially now the size of momentum space. So if I identify M with the large mass scale, like a Planck scale, then this bound is essentially the standard answer that people obtain in the calculation that I showed at the very beginning. So if you think that it's natural to bound the momentum space by the Planck scale, then of course the vacuum energy is of order, essentially, is of order of Planck energy. However, there is nothing in this calculation that actually tells you this is necessary. As a matter of fact, this calculation just telling you that this M, or the factors NP and Q, are actually three factors that must be decided by some different argument, and this argument is kind of a contextual, in a sense that in the context of the particular physical situation, we can actually fix what these numbers are. And now let me turn to this final part of this talk, in which I would actually try to find the context. And before doing that, so this is the expression that we can actually having. We see that the vacuum energy density, regularized vacuum energy density, is bounded by this expression, where N is actually the number of cells, of Planckian cells in phase space, while Q is the volume of space-time, which is proportional to the scale to power 4. Now, there is a powerful theorem. And honestly, I don't quite understand this theorem, but it nevertheless exists, which tells you that in the case of that if you quantize the finite dimensional, in this sense, a finite size phase space or compact phase space, in the sense that the number of cells is exactly in the sense that this number N is actually finite, then the dimension of Hilbert space of the resulting quantum theory is in the leading order of h bar. So for small h bar is, of course, semi-classically, is actually exactly N. And now we know that there is a one-to-one relation between the entropy and the dimension of the Hilbert space. So what I can do, I can actually understand N as the entropy of the vacuum that we've been computing. We started with computing the vacuum integral. So we computed, we found that this vacuum integral gives you this bound on the vacuum energy associated with the classical size of the compact phase space. And then this is the size of the Hilbert space, which is the size of entropy. So the vacuum carries entropy, which is in leading order, actually proportional to N. Okay, good. So now, so far we actually did it in the absence of gravity, but now let me switch gravity in a kind of a hypothetical way. And if I have a gravitating system, there is a holographic hypothesis that if I have a system of particular size gravitating, there is a maximal entropy that the system can carry, which is essentially associated with the entropy of the sitter horizon. Well, given that our universe is very close to the sitter, let me assume that the entropy of matter is close to the gravitational entropy of the sitter horizon, which scales as gravitational entropy of the horizon scales always as an area of horizon in Planck units, which is the ratio of the size of the horizon with the and the Planck length squared. Now, if I identify my n, which is the entropy of the vacuum, with the gravitational entropy, which is the bound on the entropy that can fit into the finite volume, then the vacuum energy, which is given by this bound, then n, I identify n with s, with the gravitational entropy, and then what I'm getting exactly this expression. So the vacuum energy is bounded by this expression, which is the inverse of the size of the size of the space times the square of the Planck length, and the volume, when we actually define the volume contextually in the context of cosmology, I identify the volume with the size of the horizon. So let me stress again. In general, the calculation that I did so far were completely general. I regularized the expression, but then there was a lot of freedom because I really need to associate some properties of the system like size and energy and characteristic energy with the generic system with a particular situation. Now, in the case of cosmological constant, this particular situation is a universe. And the claim is that the entropy that the vacuum has, which is again, the n is proportional or of order of the gravitational entropy, and then we get the vacuum energy having this form, bounded by this form, but then I can actually immediately compute the cosmological constant because the cosmological constant is rho times g by definition. And then g is essentially h over L Planck squared. Sorry, it's the inverse of this. Essentially, g is L Planck squared over h bar. So this cancels this term, and we find that cosmological constant is of order of inverse square of size of the horizon. And the size of the horizon, because we are close to the sitter space, so the Hubble horizon is essentially the sitter horizon. Which of course beautifully agrees with observation. And notice that something remarkable really happened, that instead of the kind of a momentum cutoff, by using this phase space reasoning, we found that the loop contribution to the cosmological constant is actually of order of, well, what the actually cosmological constant is, which is the order of the size of the inverse size of the cosmological horizon. Okay, everything fits together. The cosmological constant is small because the universe is large. Notice that if the universe was small, the cosmological constant was actually extremely big, which is something that we already know. If the cosmological constants would be positive and very large, then the universe would be very small. And now the question is it natural to expect that the universe is actually large, right? Because somehow using the cosmological context, which is the right context, of course, we actually related the fact that the cosmological constant is small to the fact that the universe is large. But is it actually natural that the universe is large? Is that any reason to expect? Well, I mean, in the spirit of this of this question, why there is something rather than nothing. Is it natural to expect that the universe is large instead of being small? And actually, there is a nice argument why we expect the universe to be large. And this argument is, well, clearly it was spelled out. It was spelled out many, many years ago in the beautiful book by Schrödinger called What is Life, in which he actually argued why the organism, like living organisms, are actually much, much larger than the size of the molecules. And the reason is the following, that if I have n degrees of freedom, then statistically, the statistical fluctuations of the n degrees of freedom are of order of square root of n. Essentially, you remember that the random walk, if I make randomly n steps, I'm essentially in the distance of square root of n from the origin. So if n is large, the fluctuations are relatively small. So the fluctuation size, the expectation fluctuation size to the size of the system goes like 1 over square root of n, which means that for a system to be stable, it's better be big. So this is of course just a hand waving argument, but it gives you kind of a taste of why we expect that the universes that are large are actually preferable. In a sense, the small universes fluctuate a lot, and that means that they are not really stable. So let me go to the conclusions, and let me just give you kind of a recap of what happened. We started with the standard vacuum energy formula. So the starting point is just a standard one. And there's semi-classical relation between vacuum energy and cosmological constant, which is essentially telling you that if I compute the vacuum energy, then I need to multiply it by Newton's constant and to get the right contribution to the Lagrangian. We noticed that the vacuum energy formula is defined in a phase space. And usually people write it in assuming that the space-time is just a large space-time and don't really care about it. And we regularize this expression, which in a sense is both ultraviolet and infrared divergent, by assuming that there is a finite number of elementary phase space cells in the system of interest. So we regularize the size of a phase space, or compactify the phase space. We identify the number of cells with the entropy using the holographic principle. And then the Sitter entropy of the universe provides us with the upper bound on the vacuum energy contribution to the cosmological constant. And this bound actually agrees with the observation. So it's not contradictory to the observation. It is more or less of the order of magnitude of what is being observed. And in conclusion, in a large universe, the vacuum energy contribution to the cosmological constant must be small. This is the first conclusion and first result, the most important result of this reasoning. Sorry, can I finish, because I just had these 2 sentences, and I will finish. The universe is large because it contains a lot of degrees of freedom, and it must have a lot of degrees of freedom in order to be by this stability argument. And that's what I wanted to say. Thank you.
Thank you very much for your talk. And now we have time for questions.
Oh, don't be shy.
So what is the measure of size of the universe in this calculation?
The size of the universe is the size of horizon.
So it's
Yeah. So Hubble radius, yes.
If you showed some transparencies before, if there was some sentence which puzzled me.
Right, okay, so
no, much farther. So,
so stop me when
no, too far.
too far.
Too far. Next. Yes, here.
Mhm.
So you said assuming that the integration does not change things substantially, but the reasoning is just that you put epsilon equals 0 in this integral. That's it, and then you have 1, and this is this inequality, and because epsilon is small, I suppose this is monotonic in epsilon, so you can write that this integral is less than 1. You agree? This integral is less than 1, or less or equal to 1. That's the result. This is as simple as possible.
Mm-hmm. Yes.
So
Yes, but hold on. That's not what matters here. Notice that there is still this parameter tau, which is essentially a modulo on the
but it's positive. Then it's positive.
It's positive.
If it is positive, there is no problem. This function in this integral is less than 1.
It is.
And the integral over
That's true. Yeah.
So it is a very simple.
Well, it is very simple, apart from a very little thing that that it's really left to be that's really left to be checked explicitly, and we try to do it, just by check it case by case, but we never did it completely. Is that assuming that this integral over tau is finite? It might be divergent, and that's the problem. So there might be.
But in this reasoning, tau is fixed. That's
No, but I need still to integrate. So to get this, I need to do the integration over tau. And the question is, so I agree.
Okay,
So tau is fixed.
This row instead of this.
This is rho of tau.
Yes,
And I need to do the integration over tau still to get
later. But this row is less than h times something to the 4. Yes? And this row depends on tau, but the
rho of tau
does not depend on.
Rho of tau is of course smaller than this one, but then if I integrate over tau, we assume that this integration over tau doesn't change this substantially, which is essentially true if this tau integration is not divergent.
So this sentence should be much farther than this inequality. That's the point.
No.
Because this row still depends on tau. You don't integrate it.
No, this is the rho. There is no tau here.
Doesn't matter, row is row.
No, this
Jurek, po prostu rho od tau jest mniejsze równe od tej. Po prostu jest takie oszacowanie, a potem możesz sobie po tau coś kuplować. Natomiast samo oszacowanie wynika z tego, że ta całka jest mniejsza równa od 1. Nic więcej. To jest proste.
Okay, dobrze.
A czym jest to bez tau?
Can we switch to English?
So this row without tau.
Our rho without tau is the integration. Okay, so
The integral.
it's the integral over.
So now, okay, so there was something physics.
With some measure or like 1 over tau.
Divided 1 over tau.
No, that's the word.
Maybe it will be simpler to show simply the slide.
Rho is by definition integral d tau over 2 tau rho without from 0 to infinity. Which means that so as long as this integral is finite, this bound essentially works up to some numerical constant. But if this integral is divergent, then we need to further regularize it. Okay, so that's the point. I agree with you that for rho of tau, this bound is of course automatic.
To jest dobrze. Znaczy to tutaj wtedy nie możesz takiego grubego szacowania robić, bo ta całkowicie jest wiesz. To jest oczywiste, logarytmicznie. No.
How do you understand that gravity is universal?
Sorry?
How do you understand that gravity is universal?
The understanding of gravity being universal is that gravity couples universally to any form of energy and momentum just by the coupling, which is essentially this one here. Right. So whichever T mu you get, in particular the T mu of vacuum. So vacuum expectation, bioenergy, momentum tensor of any field, it still couples to gravity. My point is, well, it's pretty natural that it does. My point is only that we never checked experimentally. So everybody believes it's universal.
But can we say that gravity can emerge everywhere in space, but it is not necessarily present everywhere in space?
What do you mean?
I mean that maybe there are some parts of space ripe for gravity.
But I think that this is not the point. I mean, this is not the point I'm making here. My point is that we know very well how masses and say energy produces gravity, because we have a lot of observations both in kind of a solar system experiment, cosmology agrees with that, astrophysics agrees with that. However, we don't know any direct experimental test which would show you that gravity actually couples to vacuum energy. So the only thing I'm saying, it would be actually a disaster if it doesn't. But what I'm saying is that, strictly speaking, we don't have experimental proof of that. That's the only thing I'm saying. And then I actually assume from the start of this, I assume this universality of gravity, which is essentially that whatever energy momentum tensor is, it actually equally universally couples linear, well, this linearized gravity universally actually couples to gravity in this way.
Okay. Further questions, please? Comments? Remarks? I can't hear any. So let us thank the speaker again. And we close the meeting. Goodbye.
Bye.